Hello everyone, hope you guys are doing well. On this video, I'm gonna be talking about physical properties and isomerism. So, isomerism is, we have talked about the homolog series. You guys know that the homolog series, the only difference is CH2, uh, the CH2 difference, well, one carbon and two hydrogens. For example, if I had a methane, which is CH4, and then if I have one more CH2 group, it becomes C2H6, which is ethane. And then if I add one more CH2, it'll be C3H8, which is propane. So the only difference of adding CH2 makes them a homolog series. Okay, so the physical properties change gradually along the homolog series. Like, it doesn't change all of a sudden, but it changes gradually. The longer the carbon chain in the molecule, the greater the molecular mass. We already know about this, right? So the greater the attractive force between molecules. As the longer the carbon chain, which I will explain in the next slide. So the greater attractive force, which also means that we will have higher melting, boiling point, and density. So now we're going to introduce you how it changes along the carbon numbers, and then I'm going to explain you which kind of forces we're talking about. So the physical states. I told you that as the number of carbon increases, we have greater attractive force, higher melting, boiling point, and density, right? So we have this rule of thumb that from carbon 1 to carbon 4 we have a gas state, meaning that from methane to butane, which is carbon 1 and this is carbon 4, and then from pentane, from C5 to C17 it is liquid, and C18 onwards are solid. We can see that the density increases as you increase the number of carbons, right? As you increase the density, you also know that the melting point and boiling point will increase as well, because solid will have higher melting point than liquid, right? And liquid has it higher, has melting point / boiling point higher than gas. So we know that as we increase the number of carbons increases, it will make we're going to have higher values for melting point and boiling point, and for density too. So density increases as well. The reason for this is the weak intermolecular forces. They are called van der Waals forces. And this is about the 10th grade that you guys have covered, which I will draw in the next slide. But let's finish this last bullet point. Here it says that as the alkene molecules become larger, increasing the number of carbon atoms, the intermolecular force of attraction becomes stronger. More heat energy is needed to overcome the intermolecular forces of attraction to separate the molecules, and that's why the melting and boiling points increase. So now I'm gonna show you the intermolecular force that we're talking about. It is called van der Waals force. Van der Waals force. It divides into two categories. One is London dispersion, and the other one is dipole force. So So I'll explain you what it is. So London dispersion is, let's say you have an atom where you have the nuclei, right? So the nuclei, which has positively charged, it is, let's say this is your nuclei, and then I have electron clouds. So I have electron clouds around it. So over the time, as the time goes by, we notice that some of the electrons, like this is your nuclei, some of the electrons, they gather more. So we have a more of a gathering on one side. We have more electron clouds around this area. And that's why we will have, because we know that electrons are negatively charged, we get a partially negative charge on this side because of this electron cloud. And this area of the, so this part of the atom is partially positive because this side is negative, right? This side is positive. And now this atom is attracting another atom, which is, in this case, we have more electron clouds on this side, and then so we have partially negative side here, and then partially positive side here. This is the same atoms. Let's say they are both carbon atoms. Okay, so this attracts the other one. So that's why we have a weak intermolecular force. This is a force. This is the force between two molecules, two or more molecules. Okay, so if we, as I said, normally, like we start in a neutral form, and then electron clouds are circulating around, and at one point there's more electron cloud here, so more electron clouds here, and more on this side. So it creates this positive and negative partial charges, which makes these atoms to come closer to each other, and they make the London dispersion force. While dipole force is another type. Is, for example, let's say you have this compound where you have carbon, two hydrogens, and then you have chlorine, and then chlorine. Okay, in this case we know that chlorine is more electronegative. So chlorine is more electronegative, which makes this chlorine partially negatively charged and makes carbon partially positively charged. And the chlorine is, again, because chlorine is bringing electrons closer to himself. Okay, electrons are coming closer to chlorine, making it negatively charged. And then carbon is positive, this guy is positive too. So we have right now permanent dipole. Dipole is like polarization, right? Dipole. Polarization. We have North Pole and South Pole, right? North and South. This is the same thing. Now I have here positive and negative, and negative over here, and positive here. This is polarization, but this guy always stays negative, chlorine, and carbon stays positive in here. The difference with London dispersion is that, so this negative charge in here, it might change its place. It can go into this direction. It can go into this direction. It just, as the time goes by, these charges, they change in London dispersion. So that's why these are called instantaneous. Meaning it is momentary. It happens for some time and then it goes away. So that's why London dispersion is weaker than dipole force. But altogether, London dispersion plus dipole give you van der Waals. Okay, they are altogether van der Waals forces. So this is a quick review from the 10th grade. Now we're gonna look back to it. So I told you that as the number of carbons increases, okay, as the number of carbon increases, the amount of electron increases, right? Because each carbon carries 6 electrons, and the more carbons you have, so 2 carbons will have 12, 3 carbons will have 18, and then 4 will be 24. So the more electron clouds you have, you will have a higher London dispersion force, meaning stronger this London dispersion force. So that's why now when the molecules come together, they're starting to go from gas to liquid. And as you increase electrons number from 17 to 18 and onwards, they come even closer and now they make solid. That's why we have this table in here. The London dispersion force is increasing as you increase the number of carbons. Okay? But the dipole force, you need to have electronegativity difference. So that's why I use chlorine in here. Otherwise, you need to use, for example, oxygen or other elements, okay? Okay, so now physical properties. I told you as the number of carbon atoms in the molecule increase, their melting point, boiling point, and density increases because of the London dispersion force. London dispersion increases because you have more electrons, right? In carbon 2, I told you have 12 electrons. In 4, you have 24 electrons. As it increases, you can see that the boiling point is increasing, number of carbon atoms. And let's look at here, the same thing happening with the density. Number of carbon atom increases, their densities also increase. Look at here, the density, how it is increasing as you change the carbon atoms, number of carbon atoms. Okay? Because as you know, we have liquid will have a higher density than gas, and solid will have it higher than liquid. Everything is related in this case. So now we're gonna go, this is a bit of a summary of physical properties. As the number of carbon atoms in molecule increases, they become less flammable, more difficult to burn. This is one more criteria, so you need to learn. The larger alkane molecules contain a higher percentage of carbon, and this makes it more difficult to burn. Okay? The larger alkanes also tend to produce a smokier flame due to incomplete combustion of the alkane molecules. This is for your interesting information that you need to know. So the larger alkanes, meaning that you go from carbon number when it goes from 1 to, I don't know, 17. And then the more it becomes, the more smoke it makes. Also, alkanes are insoluble in water but soluble in organic solvent. This is very important. Alkanes are insoluble. They don't dissolve in water, but soluble in organic solvents. And the reason is that because alkanes are not polar, but water is polar. If they were both polar, they will dissolve in each other. Like alkanes will be soluble in water. But because water is polar and alkanes are not polar, they only dissolve inside organic solvents. And organic solvents, they are not polar, non-polar. So it's non-polar, basically. When this is also another. So organic solvents are non-polar. That's why alkanes dissolve in them. Now, physical properties of hydrocarbons. Okay, let's continue this. This is we also have other hydrocarbons, right? We have alkanes, alkenes, alkynes, and as you see, as the number of carbon increases, see what happens. The same thing, boiling points are increasing. Negative boiling point means that they are gas. They are in gas state. The same thing happening with alkene and with alkyne as well. As you increase their number of carbons, they will have a higher boiling point. Over here, many aromatic compounds have a strong odors. We already talked about that. And they say that the shapes and size of hydrocarbons affect their boiling points. We know this, but we can't really go into that much detail of this. I told you as above, hydrocarbons are non-polar. That means that they are not soluble in water because water is polar. You know, like dissolves in alike. So polar dissolves in polar. For example, alcohol C2H5OH is polar and water is polar. That's why you can dissolve alcohol in water. They are soluble. But alkane won't dissolve in water because alkane is non-polar. Okay, some physical properties of first 20 members of straight chain alkanes. So I told you guys, so these are gas states. As you go up, it is liquid. Their melting points are increasing, boiling points are increasing, and densities are increasing as well. So from 17, it becomes solid upwards, and then melting point, boiling point, and density is increasing as well. So now let's look at the alcohols and alkanes. Before I go, I just wanted to explain you guys. So alkane is the one that we had with, for example, I have R, it's like any functional group, and then I got CH2 and CH3. When you see this, you know this is an alkane. Okay, alkane. But when you have RCH2 and when you have OH, you need to know that this functional group is alcohol. And the name of this is, for example, do you remember, we know that CH3, this is ethane, right? Ethane. And when I have CH3, 2 carbons, and then I attach OH in here, it will be ethanol. And likewise, if I'll have 3 carbons, it'll be CH2, OH will be propanol. Okay, so now if you guys take a look at this, I got alcohol and alkane. Alkane have, as you see, as the number of carbon atoms is increasing, alkane have lower boiling points than alcohols. Okay, their boiling point is lower than alcohol. Even though alkane carbon number increases, we talked about it, their boiling point increases, but it is less than alcohol. Why? I will explain it, and I talked about it in the class. It is due to the hydrogen bonding. Hydrogen bonding. You guys know that London dispersion is weaker than dipole, and dipole is weaker than hydrogen bonding. So if you remember, I told you as the number of carbon atom increases, my London dispersion force is increases, right? But alcohol have a hydrogen bonding. That's why it has a stronger bonding. That's why it will have a higher boiling point. Okay? So how the hydrogen bonding is happening? I told you the ROH group. The OH group is alcohol, right? So this oxygen in here is partially negative, and hydrogen here is partially positive. So for hydrogen bonding, you need to have this combination: nitrogen with hydrogen bond, oxygen with hydrogen bond, fluorine with the hydrogen bond. This is must have. If you don't have this, you don't have hydrogen bonding. NOF, nitrogen, oxygen, and fluorine. If you have these three bonds, you will have a hydrogen bond. So now I have oxygen and hydrogen, and this oxygen is pulling another positive. You see, this is another negative. This is positive, this is negative, this is positive, this is negative. So they are pulling each other closer and making molecules combine better. And that's why they have a higher boiling point than alkanes. You see these ones? Alcohols, as they carbon number increases, they have way higher boiling point than alkanes. So basically this is it. I will show you another version of the hydrogen bonding. For example, I have RNH2. So it is written as RNH. So NH, and then I bring another NHR. So look at here. I have nitrogen is partially negative and hydrogen is partially positive. Partially negative, partially positive. So this is pulling this. This is pulling this guy. So, and then I have a negative and positive pull on the other guy. Now I have again hydrogen bonding. I will show you another one. For example, I have hydrogen fluoride, right? And then I have another hydrogen fluoride, and then I have another hydrogen fluoride, and then I have hydrogen fluoride here. Because fluoride is the most electronegative element, and hydrogen is positively charged, fluorine is negatively charged, and this is, so fluorine, this is positive, this is negative, this is positive, this is negative, and they start, so positive attracts the negative. So this is what happening, this and this attracts each other, they make another hydrogen bonding. And hydrogen bonding is the strongest intermolecular force. It is stronger than van der Waals. Now I'm going to show you another combination, another functional group, this is called aldehyde. I will actually talk about two of them. So whenever you have R, this is anything, RCH2 and connected to COH. So you see this COH group. So this group is called aldehyde. We have it in Introduction to Organic Chemistry PowerPoint. And when you have R with CO and then R, this functional group is ketone. Okay, this is aldehyde, this is ketone. So we know how many? We know aldehydes, ketones, and then we know alcohol. So we know alcohol, we know alkanes, we know alkene, we know alkyne. Alkene, alkyne. So we know alkene, alkyne, alkane, alcohol. We know ketone and aldehydes. So now aldehydes, they don't have the aldehydes, they don't have hydrogen bonding. And do you know why? The reason is, you see this, there is oxygen in here. Yes, there is oxygen, but the oxygen is not connected to hydrogen. We need to have a direct relation within them. So oxygen and hydrogen, nitrogen and hydrogen, fluorine and hydrogen. If we have this connection, then we have hydrogen bonding. Otherwise, we don't. So this guy, the only thing that he has is, so we have here negatively charged because oxygen is partially negative, more electronegative, and then carbon is partially positive. So this makes a force called, so electrons are moving towards oxygen, makes it dipole. And the more, so we have here also carbons and carbons here, right? We have dipole. Also, we have London dispersion. Because I forgot to say it upstairs. So we have London dispersion for every molecule atom can have London dispersion, because every molecule has electron, right? The more electrons you have, the stronger is your London dispersion. But because I have oxygen in here, I also have London dispersion. Dipole. We had London dispersion on this aldehyde too, because we have all the elements and they come with electrons. But because I have this CO double bond in here, I also have dipole. So now let's continue. So aldehyde, straight chain saturated aldehydes are liquids. The higher aldehydes are solids. So straight chains are liquids. We also have alkanes in liquid state, right? Higher boiling point than alkanes. They are higher boiling point. The reason is they have dipole. Alkanes don't have dipole-dipole. Has lower boiling point than alcohols. The reason is no hydrogen bonding. If they had a hydrogen bonding, they would have a higher boiling point too. Now, these guys are soluble in both organic and water if it has less than 6 carbon atoms. So you see this aldehyde in here. I told you this side we have a polarization, right? You see this, the carbon double bond. So we have carbon and a double bond here. We have a polarization. We have a negative pole and positive. So this compound has polar characteristics. But when you have lots of carbons on this side, this side becomes nonpolar. So you have a combination of nonpolar and polar, right? But if you have more than 6 carbons on this side here, that makes it a lot more nonpolar than polar. Okay, that's why now check this back again. Soluble in both organic solvents and water if it has less than 6 carbon atoms. So if I had 6 carbon atoms on this side, I would be soluble both in polar and non-polar. But if I have more than 6 carbon atoms, I will be just soluble in organic solvent because carbons are non-polar, right? That's the reason. Now, having 6 or more carbon atoms, compounds are soluble in organic solvent. As I said, it becomes non-polar because we have such a long chain of carbons that makes it non-polar. Now, low molecular mass have pungent, penetrating, unpleasant odors. High molecular mass are more fragrant. So this is just additional information for you, so don't worry too much about it. Now, the next topic is going to be, we're going to go about the isomerism, but now I'm just going to finish off with this physical properties. So, properties of aldehydes and ketones. So I said that aldehyde is this guy, right? So I'm just going to give you examples, few of them. So CH3 and CH3, this is ethane, right? And then if I have CH3, COH, this guy is ethane, right? Ethane. And this one is aldehyde because we have the functional group in the end. And aldehyde, al is the name we use for aldehydes. This guy we have 2 carbons, right? So it'll be ethanol. Okay, and then if I have CH3 and then CO and CH3, this is ketone. Okay, ketone. And then I have here 1, 2, 3 carbon. 3 carbon, I know that it is prop, and then this will be propanon. The ending, you see, this is for ketone, and for aldehyde it will be ethanol. I'm just gonna highlight so you guys can see ketone and propanon. So intermolecular strength, I told you hydrogen bonds are stronger than dipole-dipole, and this is stronger than van der Waals. They pointed out van der Waals, but over here they want to say London dispersion because this is how it is in our book. So this is not van der Waals. London dispersion. The combination of dipole-dipole and London dispersion gives you van der Waals. Okay, hence boiling points, look at here. Alcohol will have higher boiling point than aldehyde and ketone because these guys have dipole-dipole. Alkanes have London dispersion, and alcohols have hydrogen bonding that is supporting them. Although now let's check this one. So alkane, we already know that alkane London dispersion because everybody got electrons, right? So aldehyde will have London dispersion, ketone will have London dispersion, and alcohol will have London dispersion. Now regarding the dipole-dipole attraction. Dipole-dipole attraction, I told you that you need to have more electronegative, right? So because we have carbonyl group, this double carbon group, I have here partial negative and then partial positive. So I have here polarization, right? Oxygen is withdrawing electrons closer to himself. So I have a polar bond. Polarization is happening. So that's why I have a dipole-dipole force in here too. So for aldehyde, I have a dipole-dipole as well. And then if we look at ketone, we have the same thing. We have a positive and negative, and then again there is a dipole-dipole happening because I have polarization. And for if you look at the alcohol, again oxygen is negative and positively charged, so electrons are withdrawn closer to oxygen. So alcohol has dipole-dipole too, but the thing is alcohols hydrogen bonding is so strong that this van der Waals force, dipole-dipole and London dispersion don't make that much of a difference, okay? This hydrogen bonding makes all the difference. So if you look at the boiling points right here, so alkane only have London dispersion, right? So that's why the boiling point, we have the same number of carbons on all of them. So alkane only have negative 42 boiling points, right? But look at the aldehyde. Now we have, because of the dipole, I have 49 degrees Celsius. And ketone is right now is little more than aldehyde. And alcohol is way higher than all. Now you might ask, actually before I go into that question, so once you look at here, you can see how much of a difference a dipole attraction made, right? But when you had just the hydrogen bonding and not even this guys, but you're gonna get them anyways because everybody has London dispersion, and if you have more electronegative atom, you will have dipole attraction too. But hydrogen bonding is so strong that it makes alcohol in the first place when you compare their boiling points. Okay? But there is one more thing, the difference between aldehyde and ketones. So now let's look at the structures of this guys. So I have here CH3, CH2, COH, right? And then I have CH3, I got CO and CH3. Why we have a difference? So if you look at here, we have oxygen partially negative, and this is partially positive, right? And now I have here partially negative on this oxygen and partially positive on this guy. The thing is, when you have positive on this carbon, which is closer to oxygen, and I have it here. But the difference in here is that I have a carbon on both left side, but on the right side I have hydrogen and carbon on the ketone. So this carbon, as we know, is more carbon, is more electron rich than hydrogen. So in here, carbon having positive charge means that carbon needs electron, right? But over here, hydrogen doesn't have as much as electron as carbon. While in ketone, we have a carbon which is more rich with electron. That's why this ketone is more stable and have higher boiling point than boiling point and melting point than aldehyde. Okay, so once more, I have a carbon which has a positive charge, and he needs electron, as in here. But this hydrogen that I have here doesn't have enough electron, while this carbon has more electron than the hydrogen, which is why ketone will be more stable and have higher boiling point than aldehyde. Higher boiling point and melting point than aldehyde. So when you put them in order, as you see, alcohol had the highest, then we had ketone, aldehyde, and alkane. But as you see, I have the same number of carbons. You see, I got 3, and I got 3. So when you compare, you need to have the same number of carbons so you can make a comparison. But sometimes you need to compare two compounds. Let's say CH4, and then you have another compound with C2H5OH. Okay, so this is alcohol. So in this case, you know that you have a London dispersion on this one, and then for example, this guy, you know that you also have hydrogen bonding. So of course, hydrogen bonding is stronger than London dispersion. So this guy will have a higher boiling point than this methane. Okay, so before the way we write it, so this is the alcohol condensed form. This is this is alcohol condensed form. And aldehyde condensed form is like this: CH5. This will be CHO. This is aldehyde. This is very important, guys. Aldehyde. And then ketone is looking like this: CH3, CO, CH3. And this is ketone. The way they look like. Okay? So I'm just gonna circle everything in here so you guys can use this. This is very useful information. And then, London dispersion, hydrogen bonding. Now I'm gonna go into the isomerism. Isomer is that having the same chemical formula but different bonding, shape or structural formula and properties. But we have two types of isomer. One is structural, the other one is stereo. So stereo, for you don't worry about it for now, okay? We only deal with structural isomer, which is also called constitutional isomers. So if you look at in this, guys, I have the same number of carbons, and I got here 7 plus 8 hydrogens. And if you count this one, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and then 3 carbons, and 1 oxygen in each. So they both have the same molecular formula, but they are connected in a different way. So these guys are called structural isomers. Okay? So I'll show you another types. So do you remember we have played with them in our class? So I have a butane in here. So I got a butane. I got 4 carbons. We know that butane is C4H10. It is alkane, right? CnH2n plus 2. So I got 4 carbons and 10 hydrogens. But when I connect it in a different way, now I will show you the expanded form of this. So carbon, and then I connect another carbon. Okay, so I have this. So if you see this, you could definitely see that. Now I have the same number of carbons, 1, 2, 3, 4, and then I have 10 hydrogens. It's just connected in a different way. So they are both isomers. And if you look at the pentane, pentane is C5H12, H12. And then if you count the number of carbons, 1, 2, 3, 4, 5, okay, again, the same. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The same formula, C5H12. And look at this guy, 1, 2, 3, 4, 5, C5. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, the same molecular formula, but connected in a different way. Okay, so I have some of the examples, but I just wanted to draw the line shape of this so you guys can see it. So pentane, this one is looking like this. Okay, this is the pentane. Now 2-methylbutane is looking like this. This is 2-methylbutane. And then the other one I got here is propane. So if you count the number of carbons, you could see I have 1, 2, 3, 4, 5. Now look at here, 1, 2, 3, 4, 5 again. And then this guy is 1, 2, 3, 4, 5. They're all carbon 5. And if you take a look at this ones, we have 12 hydrogens. But I'm going to show you another way to know if we have the isomer or not. But let's check out this exercises. The alkane C5H10 has 5 different structural isomers. C5H10. If you count the number of carbons in here, you see that it's carbon 5. And then if you count the number of hydrogens, you could see that it is 10. And if you check all of them down here, you would see that they're all isomers. But there is one way to figure this out. We talked about we talked about unsaturation, right? We said that alkanes are saturated, and alkenes and alkynes are not. They are unsaturated. I will show you a formula for number of unsaturation, and the formula looks like this. So N minus M over 2 plus 1. And this applies for this compound, CnHm. Okay? So I need to take into account the N is going to be number of carbons, M is going to be number of hydrogens. So let's check it for C5H10. I got here number of unsaturation. Number of unsaturation would be 5 minus 10 over 2 plus 1, which will be 1, right? And the number of unsaturation, I'm telling you, is either if you have one number of unsaturation, it means it has a double bond. If you have a number of unsaturation, which is 2, that means that you have either 2 separate double bonds or you have a triple bond. Okay, this is the 2. Also, one number of unsaturation is meaning that we have a ring, for example, like this. How it is, I'm going to show you. So, let's discuss this over here. You know the formula of cycloalkanes, right? Cycloalkane. We know that alkanes have a formula, alkane. They are saturated. Their formula is CnH2n plus 2. Cycloalkanes are CnH2n. For example, cyclopentane is C5H10. Okay? And just the pentane itself is C5H12. But you see we have 2 hydrogens lost in here. And that's the reason I tell you that a ring costs you 1 unit of unsaturation. So if you have each pair of hydrogen meaning 2 hydrogen costs you 2 hydrogen is 1 unit of unsaturation. So, for example, using the formula C5H10, it'll be, so I'm going to just name number of unsaturation like this. So N divided M over 2 plus 1, again 5 minus 10 over 2 plus 1, this will be 1, right? And then cyclopentane looks like this, right? So this ring is one number of unsaturation. So now I will give you another formula. So let's say you have C5H8. Let's find the number of unsaturation for this. It will be 5 minus 8 over 2 plus 1, which is 5 minus 4 plus 1, it'll be 2, right? So now you need to have 5 carbons, and your unsaturation unit is 2. I can draw this guy, this compound like this. I got 5 carbons, right? And I can count, and I can put 2 double bonds. Each double bond is 1 unsaturation unit. And let's count the number of hydrogens on this. If I will draw the expanded form, this would be looking like this. So I got hydrogen, I put the double bonds, and then hydrogen here, hydrogen here, and then I got hydrogen here. So let's count the number of hydrogen. 1, 2, 3, 4, 5, 6, 7, 8. You see, I got 5 carbons, 8 hydrogens. Okay, so just by knowing the number of unsaturation and their carbon numbers, I can draw another shape. How about we draw another isomer of this C5H10? So I got the 2 unsaturation, right? Can I draw the shape like this? This is 1 and then another 1. So I got 1, 2, 3, 4, 5. This is 5 carbons, right? C5. And I tell you my number of unsaturation is 2, because one is coming from the double bond, the other one is coming from the ring. Okay, so let's do the expanded form of this. So if I have carbon, and then I got carbon, double bond, carbon. So this is the way to do, guys. Firstly, write your skeleton form and then fill out with hydrogens. So I got hydrogen, then you see I got 4 bonds on each carbon, and then I fill it with hydrogen. Now count the number of hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. So you see I got C5H8. This is another isomer. So once you're asked, when they are asking you which of this compounds are isomers, first thing you do, count carbon atoms, and then find the number of unsaturation. Which will give you the right answer. So I can even do one more of the isomer. I can do 5 like this, and I can do a triple bond. This one got 5 carbons, and number of unsaturation is this, another isomer of this guy. You see, it's the same formula, C5H8. And I can do like this. This is another one. So I can even do like this. I got 4 carbons, 5 carbons, 1 ring and 1 double bond. Okay, so these are all isomers. I'm just like writing all of them here. Okay, well, that's it, guys. I think it should help you pretty much for your exam.